Hi guys, we are Group 5. We are going to talk about Maglev train. I'm the group leader, Yong Chun.
I'm Jamie. I'm Mingy.
I'm Joseph.
I'm Priyanka. And now we're going to go to the LRT station.
Hi guys, we're in a train station now. Like all train stations around the world, it is a vital link to transport people throughout their daily lives. But as we strive for an ever quicker future, the train that has been transporting us for centuries are unable to keep up. The problem? Friction. The solution? Maglev. The vision of Maglev begins at early 20th century with two men, Robert Gander and Emily Batchelor. Their dream was to develop a train system that is faster, safer, and more reliable. But what exactly makes the Maglev train move so fast? The answer lies within electromagnetism. However, currently there are two types of Maglev train. One of them is electromagnetism suspension. The other one is electrodynamic suspension. Now I will leave it to my teammates as they will explain more detail about the working principle of Maglev train.
Today we'll be talking about Lenz's law and Faraday's law, and how Faraday's law and Lenz's law will relate to Maglev train. So before that, let's talk about what is Faraday and Lenz's law first. So Faraday's law says that a changing magnetic flux will induce an electric field, and this is the formula for it. But you can just ignore the negative sign for now. That is Lenz's law. Faraday's law includes Lenz's law, which is about the direction. But let's just get into this first. So according to the definition, it is the change of magnetic flux over time. So E is EMF induced in a circuit is directly proportional to the rate of change of magnetic flux. Now Faraday's law simply says that if a closed loop of wire is placed close to a permanent magnet and a loop here, right? A magnet and a loop, then the electric current can be induced into the wire. So it means that without a power source, it's just a wire, right? Just a loop. But then using a magnet, somehow there can be current. So how do we do that? It's simply by moving either the magnet or the coil relative to each other. When the magnet is moved towards the loop, the induced current flows in one direction, but if you pull the magnet apart, the current will flow in the other direction because we are interested in which direction the current flows to. And that itself indicates the direction of current is depending on the rate of change of the field, whether the field is getting stronger or weaker as time progresses. But that is more to Lenz's law. So now I'll be talking about Lenz's law. Take a look at these three diagrams separately. So these are the magnets and the loops we've been talking about. As you can see in figure 8, there's a loop and a magnet. But because there is no motion, then nothing will be induced and nothing interesting will happen here. Now let's take a look at what happens when there is motion, relative motion between the magnet and the coil. So this one, as you can see, V is pointing downwards, indicating that the magnet is brought towards the coil, while this one, the magnet is moving away from the coil. So when the magnet is moving towards the coil will want to induce a magnetic field to oppose this magnetic field. And in order to do that, since this is moving towards the coil will have a temporary north pole here to oppose it back. And so here will be a temporary N pole, and here will be a temporary S pole. And according to right-hand Greek's rule, where your thumb will always point to the north pole, like that, the current will move this way, as you can see the current. So we have accomplished our objective of finding the direction of the current. And this is just the opposite. So when a magnet is pulled apart from the coil will want to generate a magnetic field to draw it back. So N here is moving away. So our solution is to have a temporary S pole here, as you can see, to draw it back. And right-hand grip rule, your thumb towards north, so your current will be in this way. Now let's take a look back at the definition. So the induced electromotive force generates a current, this current, which flows in such a direction as to induce a countermagnetic field that opposes this magnetic field that was initially generating the current.
Okay guys, so I'm going to talk about electromagnetic suspension. Now electromagnetic suspension is the attractive forces which are used to induce magnetic levitation. What is electromagnetic suspension to be exact is, these are the magnetic forces that are used to lift the maglev train off the rail. Now, if you can see this is actually the rail itself and this is the train. Now, this stator is located at the rail, which is at a fixed position, and the support magnet is located on the train. Now, these two magnets are actually the magnets which cause the train to actually levitate. Now, these forces are responsible for levitation and they also eliminate friction. How do they eliminate friction? It's because these two do not touch and they are controlled by super expensive computers and the system is always maintained. Now, the example of one of the electromagnetic suspension trains is the Maglev train in Shanghai. Now, this train is only used for a short distance because as the speed increases, the stability of it decreases. This Maglev train is only used to travel from the Shanghai airport to the city.
So I'm going to talk about EDS. EDS, also known as electrodynamic suspension. How EDS works is, EDS uses the repulsion of magnets to lift up the train. EDS uses superconductor magnets. What are superconductor magnets? Superconductor magnets are magnets which are cooled to negative 150 degrees Celsius to reduce the friction between the magnetic flux. There are two types of EDS train levitation. One of it is induct track, one is electrodynamic suspension. How induct track works? Induct track is basically having two same pole of magnet, one below the train and one above the track. When two of the same pole interact, they will have a repulsive force. The repulsive force will cause the train to levitate. This is a fail-safe mechanism to ensure that the train will not crash if there's a blackout. Next, I'm going to talk about the EDS. So this is EDS suspension. This is one of EDS suspension. EDS suspension is commonly used in Japan. So how does EDS work is, imagine there's a North Pole magnet, permanent North Pole magnet on the train, and this is an 8-coil magnet stick to the side of the walls of the track. How this works is, between the North Pole, there's an attractive force which levitates the train. And between the North and the South Pole, there's an attractive force to elevate the train. When these two forces combine, this will create a greater levitation force for the train to be levitated. So now I will be explaining how this 8-shaped coil works. This is a permanent magnet at the train, and this is the 8-shaped coil. To have a North Pole at the bottom end, we use the right-hand grip rule. Our thumb shows the North Pole. So to create a North Pole, the current has to flow in an anti-clockwise. And at the top, we want a South Pole. So our thumb will be facing inwards, and our finger will show a clockwise direction. So in order to make a South Pole at the top, we have to let the current flow in a clockwise direction.
While levitation explains about how the train hovers, propulsion explains about how the train moves forward. The basic principle used in propulsion is opposite poles attract and like poles repel. So here's what happens. These are the electromagnets on the guideway, and these are the superconductor magnets cooled with liquid nitrogen and liquid helium. So the South Pole over here will attract the North Pole, pulls the train forward, and the North Poles here will repel each other, thus pushing the train forward. The same thing goes to this part. The north pole here will attract the south pole, thus pulling the train forward, and the south pole here will repel, thus pushing the train forward. This results in a forward direction of the train. But here's the problem. As the train moves forward, so the north pole moves here, both the north poles will repel each other, thus pushing the train backwards, and the south pole will attract this north pole and pulls the train backwards again. So the train will move backwards again. Therefore, in order for the train to move in a one-way direction, the poles need to shift. So the south pole over here, which is initially a north pole, can attract to the north pole and pull the train forward, and the north poles here will repel each other and push the train forward. The same thing goes to this part. The north pole here attracts the south pole, pulls the train forward, and the south poles repel, push the train forward. So as the train moves forward, the poles shift and the same thing happens again. In conclusion, attractive forces pulls the train forward and repulsive forces push the train forward. For maglev train that uses electromagnetic suspension, EMS, the onboard linear motor system is able to provide both levitation and propulsion to the train. But for maglev train that uses electrodynamic suspension, EDS, propulsion coils like this are installed beside the egg-shaped coils to help propel the train forward. So how does the train accelerate and brakes? Since we know that the train moves forward through the changing magnetic poles, which is powered by a three-phase alternating current, which includes generation, transmission, and distribution, we can deduce that in order to speed up the train, we have to speed up the magnetic shift, which is also to increase the frequency of the alternating current. To brake the train, the magnetic poles need to be reversed, so that the train can brake with zero resistance.
So hi guys, I hope you're enjoying watching the video. So now I'll be talking about similarity and differences. So let's talk about the first similarity. Both of them are eco-friendly. Why do I say that? Well, as we know, maglev train uses electrical energy to propel the train forward. And electrical energy is a renewable source of energy, as we can generate electrical energy by using hydro turbine or windmill. And fossil fuel is not a renewable energy, and one day fossil fuel will be depleted. Secondly is it saves time. A passenger can get from point A to point B at a shorter time as the train travels at a faster speed. Secondly, now let's talk about differences. The first differences is the levitation methods. For EDS, the train has to be above 100 km per hour before it can levitate by using magnetic force. However, for EMS, the train can levitate even when the train is not moving. For EDS train, when the train is stationary until it reaches 100 km per hour, the train uses wheels to support its own weight. Let's talk about the second differences. Well, is operation speed. EDS travels at a faster speed than EMS. Why is that so? Well, that is because EMS tends to be unstable and the train starts to shake when it's going at a high speed, which is above 400 km per hour. This leaves safety concerns to the train conductor, as it may be unsafe for passenger and the train could derail. Another differences is EMS has a lower chance of has a lower radiation compared to EDS towards the passenger. As we know, EDS uses egg-shaped coils sticks which is built into the side of the train walls. Well, the distance between the train and the train track walls is actually quite near. So passenger may have a higher chance of getting exposed to radiation compared to EMS, as EMS, the levitation mechanism
and the propulsion mechanism is mostly at the bottom of the train. This allows a further distance between the source of energy and the passengers. So that's all for me. Now I'll pass it back to Joseph.
As you guys already know, magnetic levitation has a wide range of usage. Magnetic levitation is able to build frictionless and effective technologies. Here are some crazy technologies that the engineers and designers dream of, and they are having a project about it. The first one is building a flying city. This will greatly solve the problem of the Earth being too crowded, as the population of the Earth is increasing greatly over the years. The second uses of using magnetic levitation is to studying weightless. We can use magnetic levitation to create a room that is weightless, so that the astronauts are able to train inside the room and able to experience weightless without going to space. The next idea of using magnetic levitation is building a space launch system. This will greatly reduce the cost of traveling to space, as using magnetic levitation system is very cost effective. The next idea of using magnetic levitation is to build flying cars. This idea will greatly help the humanity, as it will reduce the emission of carbon dioxide. The last idea of using magnetic levitation concept to build a technology is building a magnetic bearing. This machine will help to support moving mechanical machines without physical contact, which is no energy loss from friction.
Conclusion: developing Maglev train system is definitely a vital choice for many countries, as it provides a faster, safer, and more reliable transportation. Thank you.
Thank you for watching.